parameters that you put in, either default or non-default, get stored here. Independently of what, you don't need to do that. That's taking care of our infrastructure. And it's good to look at them, because in many cases you may be making a mistake and adding an extra variable that nobody reads, or adding a parameter or a module that you didn't load or you didn't hook, and it doesn't get used. So if it doesn't appear here, it means that nobody used it at all. But eventually we reach the output values. Here we have some values of SimNow in the CPU 0, the values that SimNow gives us for the CPU 1, and notice that the timer value here is much bigger, because this timer has many more values. Even though we only define two particular metrics for this timer, which is the amount of cycles and the amount of instructions, this timer is linked to the memory. So here you can see that this is the amount of cycles that this particular, okay, this is not a good CPU. The main problem with this, so we have a 2 CPU core, and we run a very small application, and that application is being run on the other CPU. So this CPU is idle, so it's not the best CPU to show you the results. So we're going to go to CPU 1, which is just after CPU 0. We're going to see that this one really has cycles executed. It's executed so many cycles, and it costs... huh? Yeah, it got cycles, because the other one, so the cycles that you see in the other one are the cycles that your timer has seen. If your timer doesn't see instructions, it won't tell you anything. We may discuss a little bit later if you want, but what does it mean really? Most people that do simulation think that IPC is instructions per divided by cycles, and they don't never take into account that in many cases the CPU is waiting. And SimpliScaler doesn't wait, and most simulators don't wait. They don't have the notion of now there's no work to be done, and it doesn't matter if you go very fast on this part. Your application is 90% of the time waiting for I/O, for network, for whatever. So your speed up is not so great. And we take that into account, although not at this level. At this level, we only publish what your timer tells us. But then that information is being sent back to you. That's what one of the things that the time producer does is, if you didn't get any instructions, we're not going to believe that you went at 10 IPC, because basically you're waiting. So we're going to tell him now that this car is waiting and all this stuff. But here, what I was trying to show you is that you can get access to the whole data cache, how many data invalidations you saw, how many inclusion validations, the L2 cache, from the data cache you go to the L2 cache, to the bus, the bandwidth. So you can see here all the metrics that all these models have defined. And you can see how many updates modified, updates not found, depending on the messy here or Moisty. I think this was Moisty because it's got owner. It's got owner means it's Moisty. The O of Moisty. How many writes into the L2? How many reads you did into the data cache? And we can, for example, we can go and look. iCache reads. If we look into the iCache reads, iCache writes is 0, which is good because instruction cache doesn't, it's a nothing. And here into the iCache read, we got 254 lines read. So that those are how many reads you did into the iCache. Since this model brings the whole lines and uses the whole line into instructions, it's not exactly the same as instructions because we reuse. And many other stuff that we're going to show in this demo. Unless you have any questions. Okay, so we're going to show now another example, which is the memory trace. So, okay. All of those objects over there are what we call memory interface objects. They're programming our infrastructure the same way that we program timers. You can program your own memory interface objects. Of course, nothing prevents you from building your own memory module, your own timer that is an SMT and that gets instructions from 2 cores and simulates its own complete memory hierarchy. That's something that was our first version of PDL-Sim, used its own memory hierarchy. Then we made changes to PDL-Sim so that we could also hook our own memory modules, because if not, you're stuck with the memory modules that particular application has. But maybe you think that SimpliScaler memory modules are better than ours, or you want to change this for your own memory modules, and you don't really care about the CPU architecture. We already have capabilities to do that. And here, as an example, we're going to show you a memory module that is very, very simple. So the only thing that changed from this example to the previous blue example is that, besides the output log files and all that, of course, it's this line over here. So between the bus and the main memory, we inserted a particular object which is called memtracer that we built it. It's very simple compared to what a real memory module does. Everything that comes from above sends down, and everything that comes down, like invalidations or snooping or whatever, sends up. So it's very trivial to be programmed. It's very small. But it also produces a memory trace into a file. And this is a perfect example of if you wanted to look at any kind of any of those links and know exactly what's happening there, you can get a particular trace of that. And that trace, although this example that we're going to run here doesn't include it, memory trace. Our memory information trace has lots of information. Here we're only dumping a very small part of it. But if you, for example, have an L2 cache and you get a memory access, and if you have an L2 cache, you got all that information. But if you put a fake object like this one that basically proxies all the data up and down, you can know exactly what instruction produced that memory access, what CPU, and you can get lots of information which we're not dumping into this file. This is just mainly to get a dump back. So you could, if you're interested in saying, okay, you put your own model there and you determine, okay, why is this line being allocated over and over again? Why do I get like such a big number? Or I want to analyze this application. You know exactly what CPU and who caused that access and everything. If possible, of course. Not always you can know what CPU produced a memory access because some. Okay, and this finishes this example. Okay, so what's timing feedback? This goes back to what I said before, and I'm going to do a little bit of time here. So our simulator is functionally directed with timing feedback. What does that mean? That depends on the papers that you read in academia, because currently most simple-scalar is quite old, so nobody is building simulators as simple-scalar was building them before Tightly Couple, and they're totally more separated. Some people started calling things timing first, timing directed, functional first, functional directed. Ours is